Hello, it's Arkasha from MCAT Simplified. So we're going to be talking about E2 reactions, and E2 means elimination bimolecular. So the steps of this reaction involve, well, it's a one-step reaction, kind of like SN2 reactions. And here, a strong base, this hydroxide ion, for example, abstracts a hydrogen from a carbon that is adjacent to another carbon that has some form of leaving group. Typically, it's an alkyl halide, like in this case, where you have a bromide leaving group. And at the same time, the bromide leaving group, or whatever that leaving group may be, will exit the molecule, okay? And the electrons that are in the bond between the carbon and the abstracted hydrogen are going to move in between the carbon with the leaving group and that same carbon with the hydrogen and form a double bond. And that's what happened here, okay? Now notice that we have this delta symbol, and this suggests that this reaction is being performed in the presence of heat or increased temperature. So remember, elimination reactions, both E2 and E1, are more likely to occur when there's an increased temperature. Now, because this is, of course, a one-step reaction, this is the rate-determining step. And unlike E1 reactions, which have that carb-cation intermediate, this one, which is proceeding in one step, is going to be second order overall, and with respect to both the substrate with the leaving group and then also the base itself, okay? Now look that here we have the energy diagram, and notice that again, it's a one-step reaction, so there's only one transition state. Okay, it goes up here, high energy, and then we get the substrates. Now, some general considerations with these reactions are that this is competing with SN2 reactions, okay, which are also proceeding in one step. So for E2 reactions to be more likely than the SN2 equivalent, you're going to want to use a bulky base, okay, a really bulky base, and a strong base as well. Now, you know, in this example, the hydroxide is not very bulky, but if you had a different base, which maybe like a tert-butyl oxide, alkoxide of some sort, where you basically have, and we'll see this in a different example, where you have this very branched hydrocarbon attached to the oxygen that's doing the abstraction of the hydrogen, then that creates a lot of steric hindrance, which makes it less likely for that base to act as a nucleophile. And that's the general idea, is that elimination reactions are going to proceed more so when the base or the nucleophile is very sterically hindered. So it's less likely for it to actually get in there and be able to form a bond to a carbon. Instead, it's easier for it to take a hydrogen and proceed along the elimination pathway. And then, of course, the solvent, just like with SN2 reactions, it's going to be polar aprotic that you're going to use, okay? Now, the other consideration to note is going to be that this reaction is stereoselective. So ideally, for this reaction to occur at all, the bond between the carbon and the hydrogen, okay, specifically the hydrogen that's going to be taken by the base, needs to be antiplanar, okay? Antiplanar, or 180 degrees relative to the bond between the carbon and the leaving group, okay? And this is so that there is not a lot of steric hindrance that is introduced by having the leaving group in the same, essentially right adjacent to the hydrogen that's being abstracted. Because if it's there, those bulky bases that you're using are going to have a hard time getting close enough to take the hydrogen. So that creates a lot of high energy, which is mitigated by having the CH bond antiplanar, okay? Also, if the bond is not actually in the same plane, so if they're at 180 degrees from each other, as we'll see in these pictures here, they're still in the same plane. However, if the bond between the hydrogen and the carbon and then the bond between the other carbon and the leaving group, they're not in the same plane, like they're 90 degrees to each other, then this reaction also can't happen, because you need to have p orbitals aligned in order to form a double bond. And if the p orbitals of the two carbons are not aligned, as they would be if they're 90 degrees to each other, then no double bond can form. So this is demonstrated by these Newman diagrams here, okay, Newman projections specifically. So this is like a way of visualizing this molecule, okay, where instead of seeing it from the side, we're actually looking from this carbon, okay, back into the second carbon. So there's a carbon here, and then this carbon is right behind it. So there's the first carbon, this one, and then the second carbon is right behind it. That's what a Newman projection essentially shows. And you notice that this hydrogen is down here, and then this X group, which is the leaving group, okay, X is going to be the leaving group, is on the other carbon, and it's 180 degrees, okay, 180 away from that hydrogen. And so this would be actually antiplanar, okay? This is what is going to favor an elimination. Conversely though, if the leaving group X and then the hydrogen are on the same side like this, okay? So they're still in the same plane, so it can happen, but they're adjacent to each other instead of being 180 degrees away from each other, as demonstrated in this Newman projection here. You can see that there's going to be some steric hindrance. They're close to each other. They're actually potentially hindering each other, although the hydrogen is very small. But the issue is that when the base comes in, this X group is going to create hindrance that may prevent the base from taking this hydrogen as easily. So this is less favored. So you want it to be antiplanar, okay? Now, another consideration, okay, is that normally we said that with elimination reactions, you're going to get the Zaitsev product, okay, which is the more substituted alkene. However, if we're using a really bulky base, which is something that will be more typical for E2 reactions to like facilitate that to happen, okay, you can also get the less substituted alkene in some cases, which is called the Hofmann product, okay? So normally Zaitsev is favored, but if the base is very, very bulky, especially bulky, like for example, this oxygen with the tert-butyl group attached to it, okay? This is like a very bulky hydrocarbon chain attached to this oxygen, which is the one that's going to be abstracting hydrogens. And so that creates a lot of steric hindrance between the base that's being used and the various atoms and bonds of the molecule from which that's undergoing the reaction, okay? And that's going to make it a lot harder for this base, this very bulky base, to approach the carbon, okay, that's more substituted to take a hydrogen than it would be to approach a less substituted carbon, like a primary carbon, and take its hydrogen. So when you're using a very bulky base, it may be possible that the less substituted alkene will be the favored, aka the major product. And this can be visualized with this reaction, where you have this molecule here, okay, where the bromide is going to be the leaving group, and you're reacting it in the presence of heat, again, delta, and then this very bulky base, okay, again, with this tert-butyl group. And here, notice that when this base can come in on this carbon, okay, and it can take this hydrogen, and then a double bond will form here, as indicated by this product, or it could come in and take this hydrogen, and then you'll get this product. But look, this is a very bulky base. So it's going to be a lot harder for this to come in and take this hydrogen, because look, you have this ring structure, you have a carbon here, you have a carbon here, you have either hydrogens on this, and then you have the bromide leaving. So this is going to be harder for it to approach than if it's going to come to this methyl group here and just try to take one of its hydrogens. Okay, so in this case, this product here may actually be the major product, and that's the Hofmann product, because it's the less substituted alkene.